Hello guys, welcome to another exclusive episode of this tutorial. I trust you guys are having a nice time and also flowing with the videos we have been releasing on the flow processes and non-flow processes. And today we'll be laying emphasis on the air standard cycle. So the first on the list is the Otto cycle, which is a constant volume cycle. So what's an Otto cycle? An Otto cycle is a closed system, though it's an ideal air standard cycle for a petrol engine, gas engine, and the high speed oil engine too. So having said that, permit me to say diagrammatically we will have this. Diagrammatically I have this, okay, or rather let me use a lighter one. Let's use a lighter one. So draw it this way. Yes, and then we draw it this way too. So here is this way, this way, this way, and this way. Okay, so here we trace it down, and here trace it down too. So meaning that this is a PV diagram. So here is the first, second, third, fourth. So this is V2, which is equal to V3, and V1, which is equal to V4. Okay, now let's list out the processes involved. So as you can see from the diagram, we have that process 1 to 2, process 1 to 2 is what isentropic peak compression, okay, as a reversible adiabatic compression. So it's an adiabatic process. So process 2 to 3 is none other than a reversible constant volume heat addition. Okay, so the process 4, that's process 3 to 4, is isentropic expansion. Okay, isentropic expansion. Now process 4 to 1, is irreversible constant volume heat rejection. Okay, now we have listed out the processes involved in this diagram you can see over here. So these are the processes we are going to follow to be able to solve problems. And before the problems we are going to solve now, we would have to prove some formulas that will help us in finding a solution to some problems. So firstly, you have to note these parameters. Note these parameters, which are compression ratio. Compression ratio is denoted by R subscript V, which is equal to V1 over V2, and it's the same thing as Vs plus Vc, Vs plus Vc, okay? Vs plus Vc all over Vc, where Vs is swept volume, that's engine swept volume, okay? And Vc is the clearance volume. Okay, now Vs also, on the other hand, is given by pi d squared L over 4, where d is equal to cylinder bore, okay, where d is the cylinder bore, where d is the cylinder bore, and L is the stroke. Okay, now the efficiency of an Otto cycle is given by the efficiency, the cycle thermal efficiency of this cycle. Efficiency of this cycle is given by thermal efficiency is network over heat supplied, which is equal to Qs minus Ql over Qs, where Qs is the heat supplied, Ql is a heat rejected. Of course, the net work will be once you subtract the heat rejected from the heat supplied, whatever you get is your net work. So now, following the processes, you will have that heat supplied Qs is given by Cv. I think by now you should know the value of Cv and what Cv is, because we used it in the last video in the non-flow processes. We solved some problems with it, so in case you've forgotten, Cv is the specific heat at constant volume, okay? Then Ql is Cv T4 minus T1, okay? Now for isentropic expansion, for isentropic expansion, we have that isentropic. Okay, let's start with the compression. For isentropic compression, T2 over T1, of course, an isentropic process, equals V1 over V2 raised to power n minus 1. Okay, now for isentropic expansion, now we have that T3, which is the maximum temperature, over T4 is equal to V4 over V3 is about n minus 1. So our page, we have come to the end of the page, so we have to continue from this on another page. So I would go to another page, okay. Now but recall that from the diagram, let's go back to the diagram. So look at the diagram. V1 is equal to V4, okay, and V2 is equal to V3. So if we impute that, if you play around with the formula, we have that. Okay, I said recall that V1 is equal to V4 and V3 is equal to V2. So that means that V1 over V2 is equal to V4 over V3, which is equal to RV, since RV is equal to V1 over V2. Okay, or better still, yes, let me put it here. Let's put it here. RV is equal to this. Okay, this is 3. Or 3 is begins somehow, so we'll write it very well. So now, if that be the case, that means for our isentropic compression and expansion, the formula will look like this. So T2 over T1 will be equal to this, which becomes T2 is equal to T1 times RV raised by n minus 1. Okay, similarly, that for the expansion T3 over T4 is equal to V4 over V3 becomes T3, which is equal to T4 RV n minus 1. Okay, now remember that we said that cycle thermal efficiency, which is network over heat supplied which is Qs minus Qm all over what? Qs becomes this. Now we know the value of Qs. Qs, just like we stated before, is Cv T3 minus T2 minus Cv C, of course, a constant volume process, so everything will be CV, right? C4 minus C1 all over CV C3 minus C2. Okay, dividing through by CV into T3 minus T2, we have that efficiency is 1 minus, okay, CV T4 minus T1 all over CV T3 minus T2. Okay, CV cancels out, leaving you with T4 minus T over T3 minus T2. Okay, but we know the value of T2, which is T1 RVN minus 1, and then T3 too, same thing. So substituting this into this here, we have that efficiency is 1 minus T4 minus T1 all over T3 is T4 RVN minus 1 minus T2 is T1 RVN minus 1, and factorizing T4 minus T1 out, we have factorizing T4 minus T1 out, we have T4 minus T1, then RVN minus 1. So finally, the efficiency of an Otto cycle is given by 1 minus 1 over RV raised to power n minus 1. So we are going to be using this to find our efficiency. Note, only and only if n is equal to 1.4 generally, because they might ask you a question, and in the question they might give you the values of n at compression and at expansion. So in that manner, or in that kind of situation, this formula is not applicable. Rather, you go straight to this network overheat supplied, and then you get your answer. Okay, now having said this, let's take an example of that same question and see how it goes. Okay, now let's take that example. Let's take the example now. Yes, there we go. It's here. Now example 1. A petrol engine working on an Otto cycle has compression ratio of 8:1 and a cylinder gas temperature of 310 Kelvin at bottom dead center of the compression stroke. The law of compression, okay, is PV raised to power 1.3, which is equal to C, and expansion PV raised to power 1.2 equal to C. The maximum temperature of the cycle is 2200 Kelvin. Determine the cycle thermal efficiency. So this is a typical example of what I said in the previous page when I was emphasizing on the formula for, that is the general formula for the Otto cycle. So here we can't use that because the N, that is the compression and expansion index, are not the same. So let's see how it goes. First and foremost, you know what we do first. Yes, in case you don't know what we do first, we write our parameters given. Okay, parameters given. So solution, parameters given, parameters given. So what do we have? We have the compression ratio RV, which is equal to V1 over V2 as 8. Okay, we have the inlet temperature 310 Kelvin. Now let's write down the processes. Of course, do I really need to redraw the diagram? Okay, let's redraw the diagram. Diagrammatically, it will look like this. Okay. Okay. You don't really need to be an architect, just place it this way, and there you go. So we have this, we have this, we have this, we have this. So this, we have this, and we have this. Okay, this is PV raised to power 1.2, and this is PV raised to power 1.3. 1.3 equal to C, equal to C. Okay, this is 1, 2, 3, 4. Here V1 is equal to V4 as usual. This is your PV diagram. Here V2 is equal to V3. Alright, now for our processes, okay, in case I didn't name the processes, okay, of course I did. When I was explaining the PV diagram, we listed the processes involved, the process 1 to 2, which is the isentropic compression. So process 1, 2, which is the isentropic compression. Isentropic compression. Okay, now since we don't have pressures, P1 V1 raised by n is equal to P2 V2 raised by n, but we are not given the pressures, so rather we go straight and say T2 T1 is equal to V1 over V2 raised by n minus 1. So of course this becomes T2 is equal to what? T1 RV n minus 1. Okay, so T2 now will be 310 times 8 into, remember, n is 1.3 here, so here will be 0.3, that's n minus 1. So finally T2, after much calculation, we have it as this is T2 578.5. So the next process is process 2-3. Process 2-3. So reversible heat addition at constant volume, meaning V2 V2 is equal to V3 at this process. So from the general gas law, P2 V2 over T2 is equal to P3 V3 over T3. Okay, V2 cancels, I have this. So still here we don't have pressure, so we aren't going to use this. So we go to the next process. That's process 3-4. Process 3-4 is the isentropic expansion. So here we have that T3 is equal to T4 RV raised to power n minus 1. Of course, you already know how we got that too. Yes, that reminds us that in our parameters given, the maximum cycle temperature is T3. Why is T3? Is because if you check here, this is P. The temperature at this point is higher than any other point here. So this is the maximum. Okay, this is the maximum. So our T3 is that. So finally our T4 will be 2200 over 8 raised to power 0.2. Why? Because at this process n is 1.2, so T4 will be 1451.46 Kelvin. Alright, so it goes straight to the question. It said calculate the cycle thermal efficiency. So cycle thermal efficiency is given by network over heat supplied. So a network is the net heat, okay, over heat supplied. And of course, once the formula is reduced, we have this T4 minus T1 over T3 minus T2 times 100%. Okay, so imputing the values of the temperatures, we have that 1 minus T4 is 1451.546 minus 310 all over T3 2200 minus T2. So doing this, we have that finally this is 0.296 times 100%. So efficiency is 29.6%. Okay, 29.6%. So let's take another example to elaborate the facts, or to pinpoint and note the general facts for using the general formula 1 minus 1 over RVN minus 1, because we do not use it here. Why? Because the compression and expansion index were not the same. Okay, so let's take an example of when we have same compression and expansion index. So straight to the top, we'll go over to the next example. Okay, now example 2. An engine works at the constant, an engine works on the constant volume cycle. It has a bore of 80 millimeter, stroke of 85 millimeter. The clearance volume of the engine is 0.06 liters. That is liters though. Then the actual thermal efficiency of the engine is 22%. Determine the relative efficiency of the engine. Take N as 1.4. So as you can see here now, the N is general both for the expansion process and the compression process. So let's get down to work. Of course, the first thing is writing down your parameters. So parameters given, so parameters given, we have that we have the bore, which is D, as 80 millimeters, stroke L 85 millimeters, clearance volume VC 0.06 liters. What else? Actual thermal efficiency, so actual 22%. Alright, now recall that when we were proving and defining the terms in the first page of the Otto circle, we said that, or rather I said that, the compression ratio is given by RV, which is V1 over V2, and is equal to what? Vs plus Vc over Vc, where Vs is the swept volume, which is given by pi d squared L over 4. Now calculating pi, what is the value of D? 80 times 10 raised to power minus 3 squared. Of course it's in millimeters, but we work with our basic unit, so it has to be converted. 85 times 10 raised to power minus 3, that is the stroke over 4. Okay, so Vs finally Vs will give us 4.272 6 times 10 raised to power minus 4 meter cube. Okay, now Vc was given in the question as 0.06 liter, but liters, we don't work in liters. Okay, we work in the basic unit. So how do we convert this to meter cube? Recall from our basic knowledge of primary conversion and rates, know that 1 liter, a liter from chemistry is equal to 1000 cm cube. Okay, so in place of this liter I will write this 1 2 3. Okay, so Vc is 0.06 times 1000 cm cube. So Vc now is 60 cm cube, but that doesn't end here, it's still in cm cube. So converting this to meters, we have that 60 times 10 raised to the power minus 6 meter cube. Okay, by 60 over 1 million, I should do this conversion. So that's it, we have converted everything to the basic unit. So what is left is to find the RV, compression ratio, Vs plus Vc over Vc. Okay, imputing the values, RV is equal to what? 2726 times 10 raised to the power minus 4 plus 6, and let's yes 6 times 10 raised to the power minus 5 is the same thing as 60 times 10 raised to the power minus 6. Okay, the same thing as that. So all this in meter cube, and the VC still 6 times 10 raised to the power minus 5. Okay, yes, still the same thing as 6 times 10 raised to the minus 5 here. Meter cube, so meter cube cancels out and it leaves the compression ratio dimensionless. Okay, finally this is 8.121. So cycle thermal efficiency, the cycle thermal efficiency, which is given by, that is cycle thermal efficiency of an Otto cycle, is given by 1 minus 1 over RV raised to the power n minus 1. Okay, now imputing the value of RV that we've gotten, so we have that 1 minus 1 over 8.121 raised to the power 1.4 minus 1. So finally we have that this is 56.73%. So that doesn't end here. They didn't just ask us to calculate the cycle thermal efficiency, they asked us to determine the relative efficiency of the engine. So relative, just like relative density of something over density of water. Okay, so this will be efficiency of something over efficiency of the system. So this is how we are going to write it. Relative efficiency is what actual efficiency over cycle thermal efficiency. So the relative efficiency now, they gave us that the actual efficiency is 22%, and this is cycle thermal efficiency 56. So relative efficiency is now what? 0.3878, which means that the relative efficiency is 38.78%. So we've gotten the relative efficiency just like the question stated. So this is it. So it's not difficult, just like the other processes. Just follow the process one after the other, and also follow the parameters the way I've been given. So we have come to the end of today's tutorial. So in the next video we'll be talking about more examples of standard cycle, like the diesel cycle. Yes, okay. So in the meantime, have a nice day and thank you for watching us.
A little liquor on some ladies, yeah. We did turn up on a daily. It's how I walk up, yeah. Soft walk.